Hi, welcome to Physionic, or welcome back to Physionic if you are a longtime subscriber. Today's video is going to be discussing the cellular workings or the mechanisms by which our cells use omega-3s, omega-3 fats. So if you think of omega-3s as like fish oil or flaxseed oil, or there are other ones like walnuts, soy. Really, it depends on the type of fatty acid that we're talking about, or type of fat that we're talking about, type of omega-3 fat. So in this video, I want to go over alpha-linolenic acid, which is found in walnuts, soy, and flaxseed, as well as a few other sources as well. And what I'm going to do is trace what happens to it after you consume it. As in, I'm going to trace what happens within your cells from it entering into the cells, then where does it go, what kinds of cells it enters, and the functions that it has. What changes occur inside your cells and inside your body as a result of your consumption of omega-3s. I think this is an important concept because, if you've been following Physionic, you know that I really, really I deeply care about understanding from a macro perspective down to a micro perspective. It's one thing to know that omega-3s are beneficial to your health, for example, that they're necessary for your health, but it's an entirely different thing to then understand, well, what is happening on a molecular scale, what's happening on a cellular scale. So if somebody were to ask you, well, why is this helpful? Why do we need these omega-3s? You'd actually be able to flesh out a response like an educated human being. So this is what this video is going to be about. I'm going to be discussing some of the details in terms of where it goes, but I'm also going to discuss some of the differences between men and women in regards to omega-3 metabolism. So without further ado, let's go ahead and jump in. Actually, there is a further ado because some of you may not know who I am. My name is Nicholas Verhoeven. You may not trust what I have to say. This is going to be coming from a scientific review. All of this information is coming from a scientific review, as well as what's up here. And what is up here comes from my PhD that I'm working on as a candidate. I'm in my fourth year of my PhD in molecular medicine, and I'm also a cell biology researcher. Okay, with that out of the way, now we can get into looking at some of this information. Now, this is, as I mentioned, this is coming from a review called Metabolism of Alpha-Linolenic Acid in Humans. And I'm going to break this down with a ton of different graphics that I've created for you. So hopefully this will kind of make more sense as we go forward. And if you ever have any questions, so long as I see your comments, please feel free to leave some, and I will be happy to engage with you, ask questions, add some things that you'd like to know more about, and I'll certainly get to them as I can. Okay, so let's look at this. So I'm showing you here an image of the structure of alpha-linolenic acid. You don't really need to know this. I'm just throwing it in here because there might be some biochemistry nerds in here. So really what you need to know is that alpha-linolenic acid is an omega-3 that is 18 carbons long. And that those 18 carbons are represented here in this kind of chemical graph. I forgot what the exact name of these are, but you have each one of these, like the ends of a line is a carbon. So we've got 18 carbons here, and this is what I'm going to use as a representation of this throughout my talk here. But here we've got a fat, which is a polyunsaturated fat. The reason why we know that is because there's a kink in the diagram, which symbolizes that it is an unsaturated fat. Now, it has 18 carbons, as we can see here, and it has 3 different unsaturation points. What does that mean? Well, it means that there are 3 bonds, double bonds, that are inside of this fat. Now, here the fat is linear, that it's just a line, but here typically you do see unsaturated fats in their true state tend to be more have kind of bends in them, and they tend to occur around the unsaturated fat section. So these 3 double bonds. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons, which is why it's represented here. And then you've got these degrees of unsaturation where the double bonds are. So if you were talking about a saturated fat, you would see none of these unsaturated fat components. So it'd just be 18 and then, well, technically 0. But in this, for alpha-linolenic acid or for an omega-3 in general, and the omega-3 aspect comes from its location of the first double bond. So 1, 2, 3. So you've got this, the omega-3 starting at the third carbon. Okay, so this is the structure. All I really want you to know, I'm allowing myself some liberty on not by going into some of the biochemistry, but all you need to know is that this structure right here with this 18,3 is our alpha-linolenic acid. So you consume this in your food consumption, walnuts, flaxseed, soy, things of that nature. And some of this is also going to apply for other omega-3 fatty acids. Okay, so where do these omega-3 fatty acids then go? Well, they go towards, let me get rid of my graphic here of myself. You don't need to see me at the moment. So here we've got our fat, our alpha-linolenic acid, and that is a fat, and 1% of it, roughly 1% of it gets stored inside fat cells, and I'll touch on a little bit more on that in just a little bit. Then about 30% of that will go into beta oxidation. I will explain what beta oxidation is, but it's essentially the breakdown of fat could be used for cellular energy use, but we'll expand on that some more. And then the rest of it goes to other cell functions. And that's really what I'm trying to get at here with this video, is that these cell functions are multifaceted. And I'm going to show you within the cells what that actually is, what that does. What does the consumption of this fat do to your cells? Okay, so let's touch on this storage aspect first. So when you consume alpha-linolenic acid, I'm going to call it ALA from here on out. ALA can be stored within the fat cells themselves, about 1%. Now, that may not seem like much, and it really truly isn't in an absolute sense. 1% is about 80 grams of course it's going to shift, but 80 grams of ALA. So for a normal individual with no pathologies of any sort, normal sized man, for example, at 75 kilograms, 15% body fat, they would have about 80 grams of ALA, and that would keep him alive if he were not to consume ALA for a long period of time. He could tap into these stores of this ALA in his fat stores for almost 2 months. So it's not critical that you consume it every single day, otherwise you'll be unhealthy. But if you have a poor diet for 2 months or more, you could start seeing some of these negative effects of the loss of ALA in your system. Now, on the other hand, women, however, have a slight advantage in this regard, in that women tend to have more stored. And that's because they also hold more fat on their body. So that's the difference between for the apple-shaped individuals and pear-shaped individuals. So like a gynoid is more women, and they tend to have more fat on their system or on their body, so therefore they can store more of this ALA. And therefore, they can also, one advantage of that is that they can last longer without the consumption of ALA, so closer to a 3-month mark, while men are more towards a 2-month mark. So kind of interesting tidbits at this point. Okay, now I'd like to introduce you here to kind of the cell. A single cell, doesn't matter what cell, it can be a fat cell, can be a muscle cell, can be any other cell. And here we've got our cell membrane that circles around, and clearly is an incredibly rudimentary image, but really I don't want to get too into the weeds of, well, this isn't what a cell looks like. Let's not focus on that. This is what a cell looks like. So you've got your cell membrane that goes all the way around. You've got these 3 organelles that I'm really focused on here. One being the mitochondria, the all-powerful mitochondria, the powerhouse of the cell. Then we've got our peroxisome, which I've actually recently been releasing more videos on this particular organelle, and we're going to explain why that's important in this context. And then we've got our endoplasmic reticulum, which is close. I just threw in the nucleus here because a lot of people know where the nucleus is or what the nucleus is. So the endoplasmic reticulum is in close proximity with the nucleus. And actually, often the endoplasmic reticulum is actually also in close proximity with mitochondrion, but I digress. So the point is that we've got these three organelles within the cell, and they each have a particular function in relationship to ALA. So let's go ahead and investigate that. Okay, so the first one is after, let's say, storage was one aspect, and then the second aspect was beta oxidation that I mentioned. So you've got this ALA that's now within the cell, remember, because the mitochondrion is within the cell, therefore ALA has already entered the cell. Let me go ahead and talk to you about a little bit about how that happens. Well, you consume ALA, and then about 95% of it, the estimation is about 95% of it gets absorbed by your intestinal tract. Once it gets absorbed, it gets repackaged into different packaging molecules, for example, like chylomicrons. Those will then enter the bloodstream and will then get, the ALA will then be delivered like a bus system to all the different cells in your body, within your body that have access to the bloodstream. Then from there, it'll enter through a transporter, typically known as fat, which is actually rather ironic because it is a fat, and it will enter through a transporter that is abbreviated as FAT, called fatty acid transporter. Really simple. And then now at this point, it is within our cell. So this is where we're going to pick up. Okay, so now ALA is now enters the mitochondria, and there's a few different mechanisms that have to occur for it to enter the mitochondrion, but I won't go into those details. You get CPT1, CPT2, and the translocase. It doesn't matter. The point is that ALA enters the matrix, the very inner portion of the mitochondrion, and then here it undergoes, first it actually undergoes beta oxidation, where it starts to cleave this fat. So it starts to cut off carbons. Remember, it has 18 carbons. So beta oxidation starts to cut off these pairs of carbons from this fat molecule. And then those pairs of carbons will then enter into the Krebs cycle, or more accurately named the TCA cycle at this point. So it'll come in here as acetyl-CoA and be converted to the very first product of an enzymatic reaction. So an enzyme will come in here, interact with acetyl-CoA, interact with oxaloacetate. Wow, that was a struggle. So we'll interact with acetyl-CoA and oxaloacetate. You'll have to excuse my pronunciation of that. I'm going to butcher that the rest of the podcast. And then from there, it'll go into get turned into citric acid or citrate. And this is kind of one of the first most important aspects, is why I've got it shown here, is that this conversion by this enzyme known as citrate synthase will then allow for the production of citrate. Citrate will then get kicked out of the mitochondrion and will then be used for the generation of new fats. So yes, this omega-3 can be used then to generate more fats. It depends on the metabolic situation of the cell, but it is a possible route. So it can be used to generate saturated fat, for example. And this is the common dogma, that from citrate then gets converted to acetyl-CoA and gets produced into saturated fat outside of the mitochondrion. But assuming that doesn't happen, that the metabolic situation of the cell requires energy production, in that situation, then it'll get converted to citric acid or citrate, then isocitric acid, and it'll keep going through this kind of circular system with enzymes coming in at each one of these junctions to cause this change from one product to another product. Now, what's important here is the production of these byproducts or another product that is produced. Let's say when we move from alpha-ketoglutarate acid to succinyl-CoA, we get the production of from an NAD to an NADH. The reason why that's important is because these NADH molecules and these FADH molecules will then go and be used by the mitochondrion to generate ATP, as I've got symbolized here. So the big takeaway from all of this is that the ALA that you consume can undergo beta oxidation. As we saw, 30% will undergo beta oxidation. And after beta oxidation can enter the TCA cycle or the Krebs cycle to generate citrate for the formation of saturated fats, or will be used for ATP generation. Now, another difference between men and women, that men tend to have more of this going into beta oxidation than women. Women tend to have it more used for ACE storage, but also for cell function, as we'll discover in just a little bit. So to return back here, we just discovered how the mitochondrion interacts with the ALA. Now we're going to be discussing the effect on the endoplasmic reticulum and this interplay between the endoplasmic reticulum and the peroxisome, how they're going to kind of combine their functions together to allow us probably some of the most important, actually I would almost guarantee the most important functions of ALA. So here we've got our endoplasmic reticulum, we've got our nucleus, endoplasmic reticulum right outside of it, and here we've got a bunch of enzymatic reactions again. Now, that said, I don't want you to get scared off by all this. If you've never seen this before, don't worry about it. It's not a huge deal. I'm going to walk you through it. So here we've got our ALA. Let's say it enters the endoplasmic reticulum, and here we've got 18 carbons and 3 unsaturation points. And then here they've got the added N3 for the omega-3, the starting point. Now here what happens is you've got this interaction with all of these other enzymes, desaturase enzymes, that then lead to the removal of hydrogen from the structure of this fat molecule, ALA. And that leads to a desaturation, an unsaturation. So what is unsaturation? It is the creation of new double bonds. So now we get, from this desaturase, we then get an additional double bond. I'm just going into the biochemistry here. You don't need to know this information to understand the function, the true function. But for those nerds out there, I try to make these particular long-form videos a lot more in-depth. So if you're wondering to yourself, why am I listening to this? Does this matter? The end product is going to matter, but these functions are maybe not going to matter. Then you have the addition of 2 carbons. So then you have the lengthening of the chain. So this lengthening of this fatty acid molecule, of this fat molecule. And then you have an even greater lengthening of the chain as it continues from the addition of 2 carbons to make it from 18 to 20 carbons, and then you get another lengthening to 22, and then another lengthening to 24, and then eventually it'll be 24 carbons with 6 unsaturated sections, we'll just call it that, double bonds, and it's still an omega-3. Now this is where it's important, because this particular fat, which has been converted from this ALA, will then get kicked out of the endoplasmic reticulum and be shipped to the peroxisome. Okay, so we've got this interaction. So it's 24 carbon with 6 unsaturated bonds will then enter the peroxisome, as we can see here. And after this translocation, meaning that it moves from outside of the peroxisome into the peroxisome, then you have, as you can see, beta oxidation occurring in the peroxisome. This is the same beta oxidation, or very similar beta oxidation, that we saw with the mitochondrion. So we see the same thing here, and what it does is it starts to lob off the carbons that I talked about earlier, and it leads to the formation of a new fat. Now, why would the cell produce all these different variations of fats? Well, it depends on what it needs. In certain situations, it's going to need just a straight up ALA molecule. Let me cut to me real quick. in certain situations, it's just going to use an ALA molecule and just use it for a function that it actually needs because it needs that structure, that particular structure. In another situation, it might need a 22 carbon fat molecule, so it'll take ALA and can start to convert it into that 22 carbon molecule and then ship it out for another function. And in this situation, what it's doing is it's going through the entire metabolic sequence to create that 24 carbon molecule, then kicking it out, going to the peroxisome, and the peroxisome will then be able to further metabolize it or convert it to a 22 carbon molecule with 6 unsaturated points. So that is something that you could not, so we could not get this 22 carbon with 6 unsaturated fat points when we looked at the endoplasmic reticulum. This never happened. We got 22 and 5, we got 24 and 6, but we never got 22 and 6. So this is a unique sequence. This is a unique metabolic fate that ends up happening. And this may not happen if the cell doesn't need it, but if it does need it, then it will create this. Now, what happens after that? Well, interestingly enough, this fat will then get kicked out of the peroxisome and enter back to the endoplasmic reticulum. So why is all of this important? Well, the reason is because of a number of different reasons. So if we've got our unsaturated fat, it doesn't have to be ALA at this point. It could have been converted to another unsaturated fat. It can be used for cell membrane integrity. It can be inserted into the cell membrane. Let me show you an image of that real quick. If I can find it. There it is. So it can be inserted into the cell membrane to change how the cell membrane functions. Meaning that in a real world sense, what that can lead to is greater flexibility of that cell membrane. So if you've got a very rigid cell membrane, in certain instances that may be a good thing, but in a lot of instances that is a negative, in that you have more damage that can occur to it because it has less ability to fold and to move, to be kind of almost fluid-like. The fluidity of that cell membrane changes, and the more fluid that it is in certain instances, the better. So it can be inserted into this cell membrane. So another one is for the generation of hormones. So you can get hormone synthesis out of the unsaturated fats. You can also use it for cell signaling, meaning that you can attach these fats or aspects of these fats to different proteins, and that will change the function of that particular protein, therefore leading to a different reaction within the cell. This is important if you need, for example, an enzyme in the endoplasmic reticulum to interact or somehow send a signal to something in the mitochondrion, or for a transcription factor, a protein that's outside of the nucleus to then enter the nucleus and have an effect. That all those things are dictated by the structure of those proteins and in conjunction with, for example, a fat. So if a fat is attached, maybe that protein will do one thing, and if a fat is not attached, then it will do something else, and that is incredibly important. Another one is cholesterol synthesis. That cholesterol particles can be produced in the endoplasmic reticulum, and then ultimately, once these fats re-enter the endoplasmic reticulum, they end up getting shipped out. And be sent to another membrane or another organelle that I didn't even end up mentioning, called the Golgi apparatus. So these fats can be sent out of the ER, sent to the Golgi, and then be sent to various areas of the cell. Okay, so there's a number of different ways that omega-3s can have an effect on your cells. And these are probably the most important, because you could do away with the beta oxidation aspect, you could do away with the storage aspect, but in terms of the formation of these different fats, that is incredibly important, and that's why we have to be consuming omega-3s, because we can't generate those particular omega-3s. So some of the omega-3s that can be produced would be like EPA and DHA. Those are the fish oils that a lot of people consume. Now, ALA is not very well produced or metabolized or converted to DHA, but it does produce good amounts of EPA. And the final thing that I'll say before getting into the conclusions is that women actually have a greater capacity to use ALA for all of these different cell functions. I did mention earlier that beta oxidation is greater in men. That is probably less important. The reason is because women tend to need to produce more of these things because for childbirth, for example. So the fetal liver doesn't have sufficient of these enzymes to convert different fats from one thing to another. And in this situation, then a woman, especially with increases in estrogen, leads to much greater levels of these effects, which is a positive towards their health, but also a positive towards the fetal health. So there's an added difference between men and women. So in conclusion, even though if you've skipped to this section, you've definitely missed out on a ton of information. Alpha-linolenic acid or fatty acid or fat is more readily used for cellular functions through its conversion into multiple other unsaturated fats, as we saw through its conversion to a 20, 22, 24 carbon unsaturated fat, and this leads to its use in cell membrane integrity. So cell signaling as well, and other cell functions that are necessary for healthy life. Now, if that seems like a really generic answer, again, go back to the entire video, watch the entire video, because I go into far, far more detail than I did in that just last conclusion section. Okay, folks, hopefully you found this informative. If you did, please consider subscribing, sharing the video for people that want to know more about exactly what's happening inside their body, from the macro to the micro. That's what Physionic is all about. And with that, I hope to have the pleasure of speaking with you in the future. Have a good one. Bye.